In this module, we'll look at basic life cycle costing. Life cycle costing enables comparative cost assessments of energy efficiency projects over a period of several years. The words life cycle refer to the total time period between the acquisition of an asset and the moment that it's discarded as waste or sold on the second-hand market. A widely used metaphor to explain the essence of LCC is the iceberg phenomenon. At the moment of purchase, the decision maker seated in the boat has a clear view of only that part of the iceberg above the water surface, which merely represents the initial capital investment. However, at that very moment, he is already committing himself for a number of years to all costs below the water surface as well. Typically, when a product consumes energy and requires maintenance, the tip of the iceberg represents less than 25% of the total picture. Nevertheless, many decision makers focus exclusively on the initial investment. This module introduces LCC analyses that you can perform in a time-efficient way. It teaches you how to derive numbers that are good enough for making an informed decision, starting from a limited set of input variables. During this course, we concentrate on the first 4 steps in the 6-step analysis process set out in this slide, enabling you to perform a deterministic life cycle cost analysis. Deterministic means that using an assumption that your inputs are 100% certain, your LCC analysis provides you with one single number for easy comparison. Obviously, in the case of energy efficiency investments, inputs are seldom this straightforward. Many of the input parameters in your model will be quite uncertain or variable, like energy prices, maintenance expenses, or usage intensity, to name but a few. Specialists next perform step 5, a risk and uncertainty analysis. Taking account of uncertainty and variability requires a stochastic life cycle costing approach, which is beyond the boundaries of this course, but you can download an application note on stochastic life cycle costing from the Leonardo Energy website. In this first module, we'll look at defining the scope, identifying the relevant cost components, gathering the appropriate data, and estimating costs. In the following module, we look at the application of key financial indicators in a deterministic life cycle costing analysis. Here's an example company that we'll refer to during both modules. We'll look at the decision facing Leonard, an engineer working for a medium-sized petrochemical company, ABC Incorporated. Leonard knows that pumping systems account for over 50% of the company's annual electricity bill. He's considering replacing ABC's current pump that has an estimated 10 years of lifetime remaining with a state-of-the-art system with variable frequency drives. He can choose between 2 alternatives, A and B, with the characteristics set out on this slide. The first step facing Leonard, indeed the first step in any life cycle costing analysis, is to define the scope of the analysis. You need to define the objectives, set the time horizon, and set clear boundaries around the issue. What do you want to determine? Just how long is your long-term perspective? And what are the system boundaries? That is, on which assumptions does your analysis rest? Let's discuss these 3 elements one by one and apply the guidelines to Leonard's decision on investment in pumps. Life cycle costing analysis can be undertaken for 2 reasons: to determine accurate financial forecasts for accounting purposes, or to help reach a particular investment decision. Financial forecasting needs an accounting model that includes all possible cost factors that contribute to the total economic impact of the product or project under consideration. But the most common objective in the context of energy efficiency projects is to inform a particular decision. If the objective is to inform an investment decision, all cost factors need not be taken into account. Only the cost factors that are different between the alternatives under consideration need to be included. Once the decision for an ad hoc rather than an accounting LCC model is made, you should identify a set of mutually exclusive alternative outcomes and your decision criterion. Alternative outcomes could be, for example, different systems that can be purchased from different suppliers, or maybe upgrading or retrofitting an existing installation. Often one of the alternatives is to do nothing. It's business as usual. This is known as the base case scenario. In the ABC Petrochemicals example, the base case would be not to invest in option A or B, but to keep the old pump running for another 10 years. For his decision criterion, Leonard decides to choose the lowest total cost option from the three alternatives. Although he has firmly stated the objective of his life cycle costing analysis, Leonard is still in doubt. The old pump will need to be replaced after 10 years, so maybe he should split the base case scenario into two alternatives, replacing the old pump in 10 years with system A or B. Will they still be available at that time? If so, will they have the characteristics of today? Leonard notices that the relevance of these questions depends on the length of his time horizon. LCC analysis is all about decisions that are optimal from a long-term rather than a short-term perspective, so it's important to define just how long your time horizon is. The following 4 guidelines will help you to define your time horizon. Whatever time horizon you choose, you'll need to use the same for each alternative. The time horizon is restricted by the longest physical lifetime amongst the alternatives. The time horizon is restricted by the investment horizon of the decision maker. Some companies have a standard investment analysis period, for example 3, 5 or 10 years. Companies that are subject to considerable risks will generally have a shorter investment horizon than companies in a very stable business setting. The time horizon is shorter than the functional lifetime, which is the total time period that the functional need exists for which the product is used. Leonard must settle on one single time horizon for each of his 3 alternatives. That means he can't calculate the life cycle cost of the base case over 10 years, then LCC A over 15 years and LCC B over 20 years. He turns to the guidelines to establish the best time horizon. First, with 20 years, pump B is the alternative with the longest physical lifetime, so Leonard's time horizon will not be longer than that. Second, the company's standard investment period, he is told, is certainly less than 10 years. Who knows whether the company will still exist by then? And third, he checks how long this highly specific pumping system will be needed for operations, and he's told only 9 more years. Leonard decides to restrict the time horizon to 9 years. The problem of replacing the old pumping system after 10 years has lost its relevance, but maybe he should correct the salvage value of alternatives A and B, since they would not be even halfway through their lifetime at the end of the time horizon. After you've determined your objective and time horizon, it's advisable to write down explicitly the most important assumptions on which your analysis rests. These assumptions define your system boundaries. They determine which factors will be taken into account. Leonard has identified some important assumptions. He will consider this pumping system a separate unit. He'll acknowledge a fixed penalty cost of €50 per hour of downtime, which represents the cost of providing a backup solution, but will not consider the pump's influence on other parts of the production process. Second, he will only recognize 2 states, a fully operational pump or a fully down one. A running pump with reduced throughput is not a possibility Leonard is taking into account. He will consider the flow rate and loading factor as fixed over the entire time horizon. Third, he won't take into account consequences from unlikely events such as fire, lightning or flooding. And fourth, he assumes the salvage value of option A to be €4,000 and of option B to be €4,500 after 9 years. Once the scope of your LCC model is defined, you'll need to list all the cost components that you will take into account. In this step, there is one important rule: only include costs that differ significantly between the alternatives. Cost components can be organized into a tree structure or cost breakdown structure. Each node of the tree represents a certain phase in the life cycle of the asset. Each node has a number of sub-nodes, down to the lowest level of detail necessary for the analysis. The tree on this slide is organized into three main phases in the life cycle of an asset: the initial investment, the use phase, and the end of life phase. Here we'll ignore the effect of taxes. Therefore, any depreciation of the initial investment price within the time horizon is ignored. Leonard has identified the following cost components to be relevant in his case: the initial investment, maintenance costs, active energy consumption, downtime costs, and salvage value. Since all the other costs are about the same for the three options, Leonard will not bother about them. Before you start gathering actual cost data, it's always helpful to derive a quick and dirty LCC estimate. This will give you an initial idea of how the different cost components relate to each other. For a quick estimate, it's not even necessary to take the time value of money or inflation into account. You simply multiply the annual expenses by the number of years in the time horizon and add them to the initial investment cost with any other one-off expenses. The sole purpose of this first estimate is to guide your data gathering efforts so that you don't waste time and energy on minor issues. In our example, based on the results of Leonard's assessment, he concludes that his focus will be on energy, downtime, and maintenance costs for the different options, and he'll not waste too much time in estimations of value of salvage. The next step is data gathering. Whether you choose to rely on historical data or expert opinion, whether your choice of source is external or internal to the organization, you will face challenges. Beware of the quality of historical data such as maintenance reports, timesheets, and so on. This type of data often turns out to be far less detailed or systematically recorded than initially suggested. Try to have a clear view on what is recorded and how accurately that is done before using the data in your model. Keep an eye on the representativeness of your information. If the products you are considering to buy include new technologies or improved designs, you should think about a way to correct historical data for your assessment. The correction you decide on will be one of the assumptions on which your LCC model rests. In many cases, you will find yourself dependent on expert opinions. Here you face a particular problem that academics call estimator bias, which means that some of the experts you consult will be overly pessimistic while others will be overly optimistic. Feel free to interpret or weigh the expert opinions you're collecting. External experts can have a commercial bias. Suppliers might be overly optimistic to influence their sales process. Always try to find out how key parameters were determined and on which assumptions they rest. Some experts will produce parameter estimates with the pretended infallibility of a papal decree, while others might be circumstantially excusing themselves for their inaccuracy before giving the requested numbers. Do not assume that the self-assurance of an expert is a quality meter for the information he or she provides. Often the best experts are the ones who have an advanced technical understanding of the asset, a neutral viewpoint in relation to your decision, or an experience of working with the asset on a daily basis, service technicians for instance. The first rough LCC estimate will show you which cost components you should focus on. Once you've collected and critically evaluated the available information, it's time to find a way to make use of it. You need to determine an appropriate cost estimation method for each cost component. There are basically two approaches, a parametric or an analytical one. Parametric cost estimation is a top-down approach to cost estimation. You estimate a cost approximately by applying a relation between a limited set of input parameters and the cost. Leonard at ABC Petrochemicals used the input parameters full load power, motor efficiency, load factor, that is the average percentage at full load power, together with the annual hours of operation to calculate the pump's annual energy consumption. You can see his formula on this slide. He calculated that annual energy consumption is about 98,000 kilowatt hours for the base case, 75,000 kilowatt hours for alternative A, and 61,000 kilowatt hours for alternative B. This number can be multiplied by 12 euro cents per kilowatt hour to estimate the annual energy cost. For the downtime cost, Leonard went through a similar top-down exercise, applying the parametric cost estimation formula at the bottom of this slide. He multiplied the total operation hours of the pump times the percentage of time the pump was unavailable times the penalty cost per hour of downtime to find an annual downtime cost. Analytical cost estimation is a bottom-up approach where you start with components and look at the likelihood and cost impact of their failure. By adding the likely cost impacts for all components together, you come up with a total cost of repair. Once you've identified the potential costs for your alternatives, the next step is to compare one alternative against another to see which best meets your decision criteria. To make that comparison, you can apply three financial tools: net present value, discounted payback time, and internal rate of return. We'll look at these tools in the next module.